The Earth System, a video series for educational institutions for free use presented by the German Geological Society, the DGGV. Hello everyone. I welcome the viewers of another episode of my video series on the Earth System. This video is about Earth's magnetism, which is not only crucial for life on Earth. It has also a very special significance for plate tectonics because magnetic information, in this case the magnetic information of the Earth's magnetic field, can be stored in rocks. And we are now able to read this information and reconstruct changes in the Earth's magnetic field over the course of the Earth history. In this video, I will explain what magnetic information we measure and what we can derive from it. As with all other videos, I would like to point out the opportunity giving me feedback. If you have any questions or comments, you will find my email address on the first page of this video or on the website. The storage of magnetic information is possible because the rocks contain magnetizable minerals with a high iron content. For example, magnetite, which already reveals its special properties in its name. As we can see here, where a magnet sticks to the magnetite rock. Other minerals include hematite or pyrrhotite and some others. These minerals can store the magnetic information that is imprinted on them under certain conditions. This basically works in a similar way to magnetic hard drive storage in modern computers or tape recorders, which were still in use in the 80s or 90s of the last century. Disks or tapes with a magnetizable layer can be used as data storage medium, which are magnetized differently in different places by an applied magnetic field, which then enables the storage of data, for instance, music or tables, texts, images, etc. And something similar happens with rocks. For example, basaltic rocks formed at a spreading center from an igneous melt contain a lot of magnetite, which can store the orientation and intensity of the Earth's magnetic field at the time of its formation. To be exact, magnetic information is stored in the minerals a short time after their crystallization, namely when they cool down below a certain temperature. It is not stored immediately when they crystallize from the melt at around 1100 degrees Celsius or so. The temperature when the magnetic information is being fixed in the rocks of the oceanic crust lies between 580 and 650 degrees Celsius, depending on the mineral. And this is significantly below the melting temperature. This temperature is called the Curie temperature, named after the famous physicist and Nobel Prize winner Pierre Curie. Above this temperature, the magnetization is unstable and cannot be stored. Below, however, the information from the current magnetic field is retained, even if the Earth's magnetic field continues to affect the rock later. Of course, there is no physical rotation of small bar magnets inside the minerals. It's only the magnetic domains in the magnetizable mineral that are being aligned, and this works without the material being rotated in a physical way. Even very fine-grained sedimentary rocks can store magnetic information. However, the cooling of the minerals below the Curie temperature is not important here. During sedimentation, the fine particles slowly sink to the seabed, and during the sinking, elongated magnetic minerals are aligned parallel to the Earth's magnetic field and are embedded in the sediment in this direction. The magnetization is many times weaker than in the basalts just mentioned, but with modern magnetometers, it is now possible to read even this weak information. Let's have a look at the Earth's magnetic field. Today, we assume that the magnetic field is essentially created by strong currents in the liquid outer core of the Earth. The Earth's core consists largely of iron, and therefore we can assume that the Earth acts like a huge bar magnet around which the magnetic field is built up. This magnetic field is usually represented with the magnetic field lines, whereby the field lines are directional That means that the lines always run out of the magnetic North Pole and back into the magnetic South Pole. They are, therefore, a directional quantity and can be described as a magnetic vector. I emphasize the term magnetic North or South Pole because in this figure you can see that today's magnetic North Pole is actually close to the geographical South Pole. This is a fact that is unfortunately repeatedly misrepresented even in textbooks and many illustrations on the internet. I've even seen it as a mistake in a geophysics textbook. So let's remember that today the magnetic North Pole is near the geographical South Pole. Well, when I say the magnetic North Pole is today in the south, that suggests that it wasn't always that way. And with this, I'm addressing a phenomenon that is of great importance for the detection of plate tectonic movements, namely the reversal of magnetic polarity, or polarity reversal for short. The polarity of the Earth's magnetic field has repeatedly reversed over the course of Earth history, sometimes at short intervals, sometimes at longer intervals, as can be seen here in this magnetostratigraphic timescale. There have been around 70 polarity reversals over the last 40 million years alone, but there are also quiet phases, such as in the Cretaceous period, where there was no polarity reversal at all over a period of 20 million years. These polarity reversals are ultimately responsible for the formation of the magnetic stripe pattern in the oceanic crust. I'll explain this in more detail, how it was discovered and how it works in the next video. The stored data of the Earth's magnetic field provide us with two other pieces of information in addition to the polarity: the angle at which the magnetic vector is inclined to the Earth's surface and its deviation from the current geographical north direction also tell us something about plate tectonic changes over time. We can determine the inclination of the magnetic vector to the Earth's surface, and we can use this inclination to determine the paleolatitude of a rock where it was originally formed. If the magnetic information was not erased by heating above the Curie temperature, the angle of vector inclination can be used to roughly determine the latitude at which the examined rock was located at the time of its formation. This is possible because it can be assumed that the magnetic poles, regardless of their polarity, were always at least close to the geographical poles. And since the inclination of the magnetic vector is 90 degrees at the pole and 0 degrees at the equator, and changes systematically in between, the paleolatitude can be determined quite easily. Plate tectonic shifts in the north-south direction can be determined reasonably well if you know how old the rocks being examined are. But this does not work in the east-west direction. The longitude cannot be measured because the zero meridian is, unlike the poles, not a natural phenomenon as it is determined arbitrarily by humans. The poles, on the other hand, turn out on their own. Tectonic plates may also rotate to a greater or lesser extent when they move. This means that the orientation of the stored magnetic vector deviates from the current geographical north direction, and this deviation can also be determined. This in turn is important in order to calculate the position of the magnetic pole at the time of when the magnetic information was imprinted. These data, inclination and declination, can be used on rocks of different ages to determine the so-called apparent polar wanderpath. What is meant when we talk about the apparent polar wanderpath? We can use magnetic data of the same age measured at different locations on the same tectonic plate to determine the pole valid at that time, assuming, as I said, that the magnetic pole is on average approximately at the position of the geographical pole. However, since the plate has moved since the magnetic information was imprinted, the pole position determined in this way does no longer correspond to the current pole position. That means the pole has apparently moved with respect to the current pole position. Of course, at the time of imprinting, it was also at what was then the geographical North Pole. But because the plate was drifting away and rotating, the pole that was calculated apparently moved. Ultimately, this is again a question of the reference system. And if we do this for magnetic data of different ages, the result is the polar wanderpath, which only apparently shows that the pole has migrated. In reality, it is the plates that move, but which take the information about the pole position with them. If we carry out such studies in Europe and North America, for example, we will find that the polar wanderpaths are similar in shape, but are still far apart. If, on the other hand, we move the continents back to their position before they drifted away from each other, as can be seen here in the figure on the right, the curves overlap almost congruently. This agreement of the apparent polar wanderpath is considered one of the most important evidence for the existence of plate drift. And with that, I would like to move on to the next video, which deals with the formation of the magnetic stripe pattern in the oceanic crust and plate movements that can be derived from these stripes. This time, thanks for listening, and I'll be happy if you stick around. And I recommend continuing with the video on the development of the magnetic stripe pattern.